All right, so I gave you this one, and all I said was just we doubled the voltage. So the same thing. So I'll go red so we know what's not given. 24 volts, 24 volts. And 6, 1 over x plus 4, 1 over x equals some number, and that number 1 over x is 2.4 ohms. All right, so what is my current now? 10. What was it before?
5.
So I doubled it. So if I increase, it sounds to me like the current flow is directly proportional to the voltage of the current. Voltage, yes, thank you. So what do we have here?
4 amps.
4 amps, and this is 6 amps. Okay, try another one. See if we can make it a little harder this time. Do I have a little harder this time? Oh, there we go, right in front of me. Okay. So let's see. How about we'll clear everything off. Get some space over here. All right. We'll do 3 this time. So 3 resistors in parallel. So we've got E, I, and R once, E, I, and R twice, E, I, R, E, I, R. So this will be total 1, 2, and 3. All right, so what are my givens here? We'll go 12 volts, 3 ohms, 6 ohms, and 12 ohms, and that should be enough for you to do this. Done. Easy?
Yes.
It's either very easy or very not. Depends on where you're at. Okay, first thing you wanted to do was what? You want to do total resistance? What'd you get for total resistance? 1.71 ohms. How do I know if that's right or wrong, or at least in the ballpark?
Because it's lower than 3.
It's got to be less than 3. All right, so we got 12 volts, 12 volts, 12 volts. Just use Ohm's law to fill in the rest.
12 divided by 12 is 1.
E, I, and R. So I want I, so it's E. 12 divided by 1.714 is?
7.001.
Well, it's close to 7 amps. 12 divided by 3 is 4 amps. 2 amps and 1 amp. Oh, by the way, I came up with an analogy for why does the resistance go down as we keep adding it. We'll see if you like this one. So You ever been to San Francisco? Right. So you got to get there. You got to go over the Bay Bridge, right? So Bay Bridge has, well, at least when I was last there, they had toll booths. And a toll booth is a restriction, right? So if we got everybody from Sacramento and the whole valley is trying to get to San Francisco, and they have one toll booth open, which is a restriction, the line is going to be forever long, right?
Yeah.
They open up another toll booth, that's adding restrictions. You're adding a restrictor, but you're bringing it in parallel. Traffic starts to move a little bit easier. Bring in another one, easier yet, easier yet. And so the total resistance keeps going down as you open a booth. Now I could probably figure out that analogy even better with, one guy does 10 cars per, 5 minutes, and this guy does, and figure it out. But yeah, that get hard. But anyway, but every time you open up a new restriction, traffic moves easier. It's just easier to get through because there's not such a backlog. Okay. All right, ready for another one? All right, let me draw a different one here. All right, this one's a little different. So we got. I'm surprised one of you just doesn't raise your hand and go, what if I took the ferry instead of. How does that. Doing 3? Yeah, I'll do 3. All right, so E, I, and R. Let's try and give you the numbers real quick. So the 12 volts, 0.5 amps. We'll do 3 amps and 2.5 amps. I think that's different than what we just did. Gotta hope it is. Here, everybody finishing up already? That quick?
Yes.
My goodness. All right. Anybody want me to slow down or wait? Okay. What's the first thing you did? I total, which is? 6 amps. What'd you do next? R total, which is? 2 ohms. Now what?
12 across the board.
12 across the top. Everything has 12 volts. And then solve for R using Ohm's law. So what'd you get? 12 times half is 24 ohms. 4 ohms. 4.8 ohms. 2 is 2 smaller than the smallest resistor? Okay, sounds good to me. You ready to take it up a notch?
What's taking it up a notch?
I'm going to tell you. No, not series parallel. Okay, so here we go. This is very different. I know. Okay, so we have a 14 volt system, and that is running a motor. A motor that is a 7/8 horsepower motor that is 65% efficient. You're also running a, oops, I didn't mean to do that. I just kind of had a little 100-watt landing light bulb and a radio stack that is currently at 2 ohms. So can you solve for that, or would you like me to walk you through this?
Give us a second.
I'll give you a second.
All right, now start.
Seven over 8 horsepower or 718?
7/8 horsepower that is 65% efficient. You done?
Is this gonna be on the test?
Yes, it is actually. I think it's it's a Q&A question. By the way, when should you start your Q&A questions for the week?
Last week?
Yeah, like Monday. Want a little more time?
Yes, please.
Hey, don't forget about the Buzz's box. I gotta order them this weekend. You're not even close. Get it. It's almost done. That's your last answer, right? Yep. Okay.
The last one?
No. I wouldn't say that by a long shot.
Hey,
Yes.
Now, Buzz Box, did you ever find out how much it is now?
45.
It's 45. Okay.
50. 5.
I'll do 60. Anything lower and it's acceptable.
Okay, I'm gonna start working it if you guys want. In the back, how you guys doing? Yeah? Anybody want more time? Work it? Okay, here we go. Here on the grid, you can see this is all you can fill in. You know it's 14 volts, you know it's 100 watts, and you know you got 2 ohms. All this mess here, you got nothing out of that that's usable right now to fill in this grid. Okay? So let's take a look at this right here. I'm going to scroll down, we'll come back up, but we have to solve for that motor, which is really the key to this whole thing. So I said that it's a 7/8 horsepower that's 65% efficient. What does that mean? Well, 1 horsepower is 746 watts. So we can solve for that watt there on the bottom, but we got to figure this out. So here we have a 746 watts is 1 horsepower, but it's a 7/8 horsepower. Now when we talk about something like this, motors are rated in the output. So that's the work that it can perform. It can perform 7/8 of a horsepower. If it was 100% efficient, it means that, well, let's take it back. If I had a 1 horsepower that was 100% efficient, that means 1 horsepower in equals 1 horsepower out. Okay? If I had a 7/8 horsepower that was 100% efficient, that would mean 7/8 in of 7/8 of a horsepower in, or let me back up a little bit. I could have did a better job. 1 horsepower, if it's 100% efficient, that means 1 horsepower in equals 1 horsepower out, which is to say that 746 watts in would equal 1 horsepower out, or 746 watts in equals 746 watts out. Do you follow that? Okay. But we're not dealing with 1 horsepower. We have a 7/8 horsepower. So what is 7/8 horsepower? Okay, so that's 7/8 times 746, which equals 652.75 what? Watts. Okay. That's great. So that's the output. What's the input? So again, a ratio, if 652.75 watts is my output, right? And that is, let me see, I need to know what my input is. So this is the output. My output is, I have notes here. I kind of don't like my notes here. That's why I'm stumbling over this. I'm like, yeah. So I just wanted to, I don't like the way I set it up here. I was just wondering, can I set up a different way and explain a little bit better? You have to end up multiplying 65 times x. So if 672 watts, yeah, that's what I was going to say. Looking at it, I want to set this up as 100%, but you got to be careful how you do it. If that's 100%, what is 65%? I don't think that's going to work out the way I wanted it to.
Well, isn't the 652 65% efficient?
That is your,
Oh, no, that would be 7/8. That'd be your 7/8. So you got to find 65% of 652.
I want to explain it really carefully. That's why I'm just, I'll just do it. I wrote it down in my notes, even though at first it may not make much sense. But we could look at it this way. If 652.7 is the 65%, then what is the 100%? What is the input? And it does work out that way quite well. So it is then 652.75 equals 0.65x, divide both sides by 0.65, 0.65. You're going to end up with x equals 1004.2. Now, the way you want to check this, the input is 1004.2.
You have to put that in order to get that output because it's.
Okay, remember, the motor is 65% efficient. You've got to put in a lot more power than what you're going to get out. So if I put in 1,000 watts, I'm going to get out 652. Because you're going to have bearing loss, friction loss, motor loss. Hannah's crinkling her face.
You probably multiplied by 0.65. You should multiply by 1.65.
All right, so
Wait to get 165%?
Yeah.
No, that's.
you want me to do it again? I don't know how to. Can do it slower, but follow me on this. And this is where you can. I want to say that okay, you can set up a ratio, and sometimes you can do a trial and error. It's okay. It's okay to do trial and error. So let's just say we don't know. All right, and we'll go. Okay, well we know. What do we know? We know it's 652.75, and we know it's 65% efficient. Okay, so we could set it up and say, well, if this 652.5 is 100%, what is 65%? Now, does that sound right to you? Okay, and the reason why it would not sound right, or you can go with it, then you get 1x equals 652. Yeah, 652 times 0.65 equals 423.8. Everybody know where I'm going with this, right? Okay, so I did this down here. This is a whole other thing. I'm trying it all over again. I say, okay, so my two numbers now are 652, and that's my output, and my input then is 423.8 watts. How efficient is that motor?
That thing is.
Wait a minute.
That's
If I'm
extra.
putting in 423 watts and getting out 652, you just solved world hunger, crisis, everything. You solved perpetual motion.
Coder.
Okay, so can that be the answer? No. So you just got to cross that out. Go, that did not sound right. Half of these questions, it's just, does that sound right? Right? And that's where I'm always harp on you. Don't just do the paper. Think about what you're doing, right? And what should this be? Figure it out in your mind. And that's why, okay, so you can say, well, that was totally not it. You know, so if you ended up doing something like that, I'm going to scroll down so we get rid of the top. You do something like that, well, that's totally not it. Okay, well, what can I do to make this work? Well, I can just try rearranging a couple things. So I still know it's 652.75. Okay, and I still know that up here is going to be the number I'm looking for. And I tried 100 on this side. Well, now what do? Try 100 on this side, okay, and 65 on this side. See if that works for you. Oops, that's going to be 1.0 and 0.65. Okay, and then I go, all right, 652.75 times 1 is 652.75, and that equals 0.65x. Divide both sides by 65. 0.65, 0.65, and I ended up with x equals 1004.2. And I say, okay, so if I have 1004.2 watts in, and I have 652.75 out, does that sound like a motor that is 65% efficient? I can try it. 1004.2 times 65 65% equals, oh my gosh, it's 652.7. So there we go. So everybody followed that? Because if you did it and you're like, I hope I just dream it and get it, it's on the test. I think at least several times. Okay, so now we know that. What's my number? 1004.2 watts. 1004.2.
And you want the end, not the output, right?
I don't care about the output anymore.
Okay.
I want to know how much my circuit is sucking down. So that means this was 1004.2, right? Okay, so now I'm getting somewhere. So what else can I do here? Well, I can go, oops, I should put in blue what we're getting. 1004.2. We know this is 14 volts. We know this is 14 volts. We know this is 14 volts. All right, what else can I do here? What's that?
Solve for current.
Solve for current. Okay, how are you going to solve for current?
Resistor 4. Or 3, yeah.
R3?
Yeah.
Okay, you're going to solve for current. All right, so what is my current here? 7 amps. What's it here? If you say 7 amps, you're wrong. I get my watts though, can't I?
Yeah.
How many watts do I have here? 98. 14 times 7 equals 98 watts. Now what can I solve for? Power total. Okay, so power total is P1 plus P2 plus P3. So what is my power total?
1202.
1202.
2.3. Or sorry, 0.2. Excuse me.
Uh-oh.
02.2.
Okay, watts. Now what can I solve for?
Solve for I of resistor 2. Or
I can solve for I right here. So remember, it's P, P, I, E. So I want to solve for I, so it's P divided by E.
Yeah, I screwed up on the motor stuff, my total and the motor.
Oh, okay. You guys following along? I feel like I'm all by myself suddenly. What are we working on right now?
Solving for current on the total.
Solving for current on the total. What do we get? It's P, I, E. I equals P divided by E.
85.870.
85.87. 85.87 amps. Okay, now I can get our total.
0.16302.
0.16. 0.16 ohms. All right, whew, man. We got 2 spaces left over. This is looking a little difficult now. Or is it not? It's not. What can I do now?
Divide 1,400.2 by 14.
I can get I because of pi, because we like pi. So it's 1004.2 P divided by E. What do I get? Hannah.
1.7.
Hannah, what?
71.7.
71.7. What do I got here?
7.1.
7.1. Okay, all we got to do is do now Ohm's law to find the resistance. What do we got?
0.2 ohms.
0.2 ohms.
1.97 ohms.
1.97 ohms. Okay, is 0.16 smaller than the smallest resistor? Looks like it. There's the smallest. That's less. Let's try it out. Let's just see if we're right before we move on to the next question. So 0.2 x minus 1 plus 1.97 x minus 1 plus 2 x minus 1 equals 6 and some change. X minus 1 equals 0.16645. That's pretty dang close right there. Okay, that was easy. Everybody got it? Yeah?
I
after you explained it.
Well, that's why I'm here.
The motor part was the only thing that
Yeah.
caught me.
Well, of
I
course.
did it backwards, and so.
Of course. Yeah, and that's okay. You just remember to ask yourself, did that make sense what I just did? You know, because it will. What most people are going to do is multiply 7/8 times 0.65 and get that answer and just go, oh, there we go, you know, so, yeah.
So why exactly do you divide by 0.65?
Because motors are always rated in output,
Not input.
not input. But we're doing a circuit, and we're like engineers trying to figure out what this is going to draw. And honestly, this is the job of an A&P. This isn't just some esoteric kind of, I don't know. Granted, in a production aircraft, you don't get to just make up stuff. I don't see too many instances where you would be just throwing in a 7/8 horsepower motor. But as I say that, back in the day when I was new in the field, we could do crazy stuff like this. And I did crazy stuff like this. You get somebody who would come in, oh, you can because you're working in, you're not CAL FIRE, you're,
Airstrike?
yeah, but you guys are actually not government aircraft. But if you're working government aircraft, let's say you got a contract to work on CHP's aircraft, which we used to, and they come in and, you know, CHP guys, they're wearing their helmet, their flight suits, their weapons, their boots. And this is back when they're flying 206s, man, they didn't like to be hot. They wanted an air conditioning system. And you're used to your cars where your air conditioning compressor is run off the engine. Well, they do that in aircraft that have factory air conditioning. But the easiest way to add air conditioning would be to add a compressor in the back with an electric motor. So here we go. So you are assigned this job, and you are supposed to put a motor back in the baggage compartment, a 7/8 horsepower motor that's going to drive an the compressor for the air conditioning system. And by the way, they want a 100-watt light bulb to do something and a 2-ohm whatever. You know, maybe it's a little speaker or something that enunciate, or you know, a 100-watt light to tell you when the air conditioner's on, and you know, a 2-ohm resistor there for something. So you would actually do this. So you would what's that?
For the vents?
The vents, there you go. Yeah, it's a vent motor or something. All right. So what we would do then is we would do this. I would sit down on a piece of paper and I would say, okay, it looks like this. We got a 14-volt system. I've got this motor, this watt. I would do this electrical analysis. I would have to put it on a form 337, which is a major alteration repair form. And then what you would do from this point, you would evaluate the circuit and you'd say, okay, I'm running 14 volts at 71.7 amps. Then you would take the run, how long it's going to go from your source, your battery, to the motor, right? And of course, I would have relays in there to operate this and all kinds of stuff, and you'd figure that out. And then you would figure out, based upon the load and how far the run is, what size wire you had to use. Because you can't just pick a wire, right? It's like, well, I don't know, I like the blue wire, it sounds good. No, you got to pick the right size wire. You're going to create smoke in the cockpit. And so you would do that, put it all together, and then together with this load analysis, based upon the rest of the aircraft, you would submit this to the FAA. And back in the day, they used to do this thing called field approval. I mean, I remember days where I would have an airplane, I had one low-wing airplane, and their Form 337, major alteration repair, and I had them taped to the wing, all the way from the root to the wingtip, with stuff that this aircraft had done to it that was just not approved, crazy stuff. It was this Globe Swift. It had Cessna seats put in it. It had the angle of incidence on the tail changed. It had the stall strips had been shortened. They put on Cleveland wheels and brakes that were never approved. It just went on and on and on, you know, and customer bought it. I did a pre-purchase, said, do not buy this airplane. And he did anyway. And said, well, now I got to do all this. And the FAA would come out back in the day and they would look at it and scratch something. And if it made sense, they would just stamp, I'll buy it. And they would sign it off, called a field approval. And they could approve anything in the world. I mean, it was crazy. It was the good old days, man. It was so fun. And let's get a field approval. I mean, think of the craziest thing you want to do, you know. If you can get an FAA guy to come out and buy it off, he'd do it. Well, then their legal department got involved and said, well, now wait a minute here. You know, you sign that off as an FAA inspector and the plane crashes, the family goes to the federal government, says you signed off and approved that, and that may have caused an accident, so they kind of did away with that. So I haven't heard of a field approval in the last 20 plus years. But we used to do that all the time. And this would have been part of it, to do something like that. So nowadays you work with a designated engineering representative. It's very expensive, and you get engineering data, and it makes the airplane safer. Yeah.
So essentially, whenever you do proportion for like the motor,
Yeah.
whenever you figure out the loss, that's 65% output to the 100% input.
Uh-huh.
Okay, just making
Yes.
sure.
So the thing that I'm confused about is, just how exactly to put the ratio, because when we first started with the ratio problems, like converting knots to miles per hour,
Yeah.
it would be 100 knots over 160 knots is equal to 115 miles per hour over the bigger miles per hour that you didn't know. And, in my head, I'd be, I would put it like, okay, on one side of the equation, we'll have all of one unit measurement, and the other side will have the other side, but it doesn't work for this one for some reason.
I know, and that's why I was sitting here for a second quiet going, how do I explain this one to him? Using the ratio problem. Let me think about
So I
something
try to
here.
stick to that rule, just to make it easier for myself, but it just won't work for this one. That's what's going on.
I wonder, okay,
Like the year.
you could, I don't want to say it, it's not an inverse. What if you went 600 now we're in green, 652.75. Let me see. I was going to go, you have to multiply it by, no matter how you do it, that's my 100%. That's my 100%. So,
652.75 over X equals 75% over 100%.
it can't, 652 has to be 1, and X
I tried that.
X has to be 65, and that's why I came down to this down here, and I said sometimes, because I told you every single problem we just done is a ratio, and I said sometimes you can trial and error it out. Let me think this one through here. 652 is the output. Output over 65% is the out over X is in. Nope, because 100 is still out. You'd have 100%. Where's that in? I don't have a good answer off the top of my head.
100%, might be in.
Yeah, 100% is in. There we go.
Okay.
It is.
So I was saying earlier.
Yeah.
Well, say it louder and say it prouder. Stand up.
Take that.
Did you say that earlier?
No, that's not us.
Okay.
No, that's right.
Well,
That is-
okay, I'll be honest. I heard her, and then I just played dumb for a minute so I could be like, I all made this up. But she caught me and called me on it. Thank you. So in, out, out. Got your innies and your outies.
Innies and outies.
That's what it is. Innies and outies. Okay, so that means that I can give you. So tomorrow we're going to do series parallel, which they're definitely a little trickier. They're not. I think they're really easy.
Just misunderstood.
They're just misunderstood.
Okay.
So I can give you a quiz on parallel circuits tomorrow. They're very similar to what we just did. The trick is, and what I didn't do today is throw in really milliamps as a starting point, or kilo ohms. So make sure that you're very aware of converting millis and kilos into the right format. All right.